We have this cool topic now, which is vehicular networking. I'm very excited about this because, well, I've already heard some of these talks a little bit anyway, and they're really nifty. We have two speakers today. Christoph Sommer is an assistant professor at the University of Paderborn. He's part of the Embedded Systems Group, and his research is focused on questions regarding traffic efficiency, safety, and security aspects of car-to-X communication in heterogeneous environments. William Whyte is chief scientist at Security Innovation and the technical editor of the IEEE standard 1609.2, specifying communication security mechanisms for vehicle-to-vehicle and other communications. He has been involved in the cryptographic standards group IEEE 1363 and ANSI X9F1, and he has contributed to the CFRG and the IETF TLS working group. After their presentations, the IAB's Russ Housley is going to moderate the discussion, so I would like to welcome Christoph and William and Russ.
It is my absolute pleasure to shine today a light on a topic that I think hasn't received nearly as much attention as it should have, which is vehicular networking, wireless networks of vehicles driving on the road. And by way of a motivating example, consider this example where we have a blue car driving down the road, and the idea here is to have the vehicle driving two cars in front of the blue vehicle brake sharply. And the outcome of this situation should be pretty clear. It will be too late for any of the other vehicles involved in this to react, especially for the blue car, with the outcome that we will get a crash, possible injury, possible loss of life even. And now the solution is obvious. The solution is to warn the driver or to warn the vehicle if it is the vehicle that is driving. And the way to do this is wireless communication. The exchange of information may be broadcast by the vehicle that is braking sharply, maybe even broadcast by the obstacle because of which the vehicle is braking sharply. And all of these concepts are not really new. This goes back to the 1970s, actually, where we had bold ideas already of visionary infrastructureless solution, visionary ideas of highway automation. But all of these ideas at that time were simply unsupported by the technology that was available to us. So there was early interest, even by industry, but absolutely no market success of these systems. And this stayed for quite a while until the 80s, where we had a paradigm shift. Things moved away from being infrastructure-less to being infrastructure-assisted now, from complete highway automation to not much than just driver advisory. And one of these systems you can see on the top right corner, where we have a traffic light equipped with an infrared beacon that is informing the driver of upcoming traffic light phases and makes it possible for the driver to adapt to kind of a green wave situation. But this has an obvious downside, which is if we do this transition to infrastructure-assisted systems, infrastructure needs to be in place for the system to work. So that means we have kind of a chicken and egg type of standoff, where without deployed traffic lights in that case, nobody wants to buy the system. With nobody buying the system, there is no incentive to equip more traffic lights. So again, things stalled until the 90s, where we had new cellular technology. Cellular mobile networking made it possible to have this infrastructure then, to be able to disseminate information to cars. And this is actually where we had the first very early car-to-X systems that were informing drivers of certain things, but made it possible to have an upstream back to the internet in that case. And these examples are the ever-famous OnStar, 1995, BMW Assist, and many, many more that followed. But this made vehicles dependent on a cellular network for providing these services. So again, little things changed until the 2000s, when a sharp increase in computing power made it possible to now deploy fully distributed and highly reactive ad hoc systems. Cars directly communicating to other cars on the road. And this triggered a number of activities. So in the late 2000s, lots of coordinated research programs sprang up, memoranda of understanding, of cooperation in the next years between the three biggest car manufacturers, between Europe, US, and Japan, trilateral agreements, which culminated in a lot of numerous and large-scale field trials that tried out this technology in kind of a close-to-market scenario and concluded that this technology is hugely beneficial. The NHTSA predicted that two very simple applications alone, intersection movement assist and left turn assist, could prevent some 100,000 crashes and save 1,000 lives annually if this system were to be deployed. And this is where we are now. This triggered the NHTSA in August 2014, so roughly a year ago, to actually say they were going to propose rulemaking, in IATF parlance a must. New vehicles must be equipped with that kind of technology, vehicular networking, to be allowed to operate on US roads. And in fact, there are early commitments by car manufacturers to, by 2017, equip new models with that technology. So this is to come. This is technology that will be deployed on the roads. And it fuses very nicely with a second trend. And the second trend is that autonomous driving is moving from being purely academic, playing around with equipped cars, to being very, very close to market. You all know the Google car and the many cars that follow, the many cars that are right now driving on the roads. And that fuses autonomous driving and cooperative driving, which is what vehicular networking brings us, to build something like automatic driving, platooning, where we have one truck driving in front that is still steered by a human, and all of the other cars in the platoon following just centimeters apart, autonomously following this one car, made possible by vehicular networking to be able to react in time to all of the acceleration, deceleration, steering of the truck leading the platoon. Now these are the applications. This is the motivation. What makes this work, obviously, is networking. This is why we're here. And it can be argued that vehicular networking represents a third evolutionary step in networking as we know it. We used to come from traditional networks, wired, non-moving, statically configured, to the ever-present mobile ad hoc networks, now wireless, now mobile, now dynamically configured, now to vehicular networking, which is a completely new field of deployment. And indeed, the first way of casting vehicular networks was as vehicular ad hoc networks, so as a pure application of mobile ad hoc networking principles to vehiculars. This turned out to not work so well, and now there is a gap to fill. And this gap has been filled on the lower layers already, and is commonly termed DSRC, dedicated short-range communication after the frequency band in the US that this is operating on, which is kind of our new lower layers that we can build on. And the first idea was to simply adopt technology that is already there, to adopt Wi-Fi technology, wireless LAN, 11A, B, G, N, which turned out to be not so good a fit. Mostly because they were designed to operate in one of two modes that are mutually exclusive, infrastructure mode and ad hoc mode. And the switching between those modes and the association to basic service sets is very time consuming, actually taking a lot of the time more in terms of association time than is being afforded by the very short communication opportunities that two vehicles might have on the road. There's also problems of massively shared spectrum. This is operating in the ISM band. And of course, lots of physical layer effects that just make everything break apart. So what was done is wireless LAN was extended. Wireless LAN has a lot of extensions, and so what has been done is just to form a new standard, DSRC. Lots of these extensions have again been collected to form a new basis, and one of these extensions obviously is 11E, quality of service. Higher priority frames are sent sooner on the channel. 11J, half-clocked operation, a more robust way of encoding frames at just 10 megahertz of bandwidth, which makes this operate in harsher environments. And the very, very new 11P standard, an OFDM file layer that was designed for operation at 5.9 gigahertz in the DSRC band. And an amendment to the standard that brings with it a completely new operation mode, called OCB mode, outside the context of a basic service set. And this makes the standard work. OCB mode, very simply put, is simply allowing devices to, at all times, transmit frames addressed to a wildcard basic service set. That makes it possible to communicate without any association process. Simply broadcast the frame and hope for the best. But of course, this shifts coordination from the Mac to the applications. Now there needs to be something in place that coordinates when frames are being sent on what channel, and when devices are listening on that channel. And this is important because there are many channels to pick from. There are at least 5 channels in the US and in Europe each, allocated only to vehicular communication. That is reserved. Nothing else may communicate there. At no license cost, but very strict usage rules in the sense that only vehicular networking can operate there. So that means there's new approaches to be sought there also. And if we think about information exchange on the higher layers, one might think that this is something that can be addressed with traditional protocols, for example with routing. But if we consider the applications that are supposed to be deployed on vehicular networks, it becomes very obvious that this will be hard to do. Consider all of the safety applications that are purely one-hop broadcast information dissemination. This is where safety is very relevant. Routing is simply way, way, way too much overhead to make this work in the very short term. But also think about non-safety applications like traffic information systems, where such a system might really shine. Here, routing will simply lead to the system not scaling well enough because information has to adapt to different granularities, to incorporate updates as the information is traveling through the network. So also here, routing is not applicable. And that leaves a small subset of in that case, I called it comfort applications, where we can actually do streaming of data to the cars. But even for a small subset of those, the ones that disseminate information in a very near field, routing is just inapplicable. It will be too slow, it will be too much effort in terms of data overhead wasted. So we have a lot of blank space to fill up, a lot of blank space for protocols to be deployed that make this system work again. And these protocols are there. They have been researched in the past years. It's just a necessity to assemble them into a complete stack. And this stack needs to meet a lot of old challenges. Nothing new in wireless here. Multicast communication, low load, low delay, we all want that. But there's several new challenges to be met as well. Highly dynamic topology, safety, partitioning of the network being the norm rather than the exception. Fragmented networks still operating as they should. Very complex mobility patterns, high-speed mobility, but at the same time very predictable mobility, are also things that can be exploited and have to be addressed. And in fact, there are 3 standards that are addressing these challenges. In the US, that is IEEE 1609 Wave. In Europe, that's ETSI ITS. And in Japan, that's RFT 109. And I want to take some minutes to briefly introduce these standards to you. Let's start with IEEE Wave. That is the US standard. The idea here is pretty simple. The idea here is to take to a large degree, unmodified protocol stack. To say we probably have only one physical layer, we might have 2 physical layers. On top of that is the standard wireless LAN MAC. On top of that, a new layer is introduced, channel coordination. That is the layer that makes sure that we are tuned to the right frequency at the right time. And then on top of all of this, a new protocol is deployed, Wave Short Message Protocol, something that is very lightweight, that makes it possible to exchange data with little overhead. Now you see on the left-hand side, TCP over IPv6, that is still standardized, that is still possible, but it's not really in the scope of this standard. So what does channel coordination do? Channel coordination's job is to make sure that even with just one radio, it is still possible to receive critical information. And that is made possible in IEEE Wave by recommending that devices tune to a well-known channel called the control channel at periodic intervals synchronized over all devices. So the default interval is 100 milliseconds for all of the devices to tune to a well-known channel and exchange information there. And this control channel is then used to disseminate these high priority information, to disseminate service announcements of services that then are being operated on all of the other channels, the service channels. And that brings with it a lot of problems. Synchronization effects by the channel switching that are being addressed in more recent iterations of the standard, but they are still present in there. So the European standard at CITS went a little bit of a different route. The motivation was to learn from the lessons of WAVE, to not specify alternating access to the control channel, but instead to focus much more on multi-radio. And one of the core recommendations that is given is, if you only have one radio, you better leave this tuned to the control channel at all times. If you have more than one radio, you are fine to use the service channels for whatever you want, but if you just have one radio, you keep it on the control channel. The stack is also much more mature, but also much more fully featured in the sense that it proposes a lot of facilities, a lot of services that are already operating standardized on the stack, one of which is cooperative awareness messages, periodic, up to 10 Hertz, depending on the situation, safety messages that are being disseminated and are supposed to inform a vehicle driving about the state of surrounding vehicles, to inform them about speed and location of the vehicles. Second big component is a cross-layer component in CITS, which is the decentralized congestion control component, whose job it is to regulate locally access to the channel, to monitor the state of the channel, and if the channel is being sensed to be very busy, to keep local applications from accessing the channel too frequently or with too much transmit power or with less than optimal modulation coding schemes. And that is a core component of the stack. The second core component of the stack is geonetworking, which makes it possible to disseminate information addressed to a topologically scoped set of vehicles. The simplest one is the topologically scoped broadcast, a simple N-hop neighborhood flooding, informing cars driving 2 hops away from me of certain information that they might be interested in. There's also geo-broadcast, where I push information to a certain point addressed by longitude, latitude, and a shape, and then disseminate it in that area. And there's also geo-unicast, where I route information to exactly one car and one car only, and I help this routing process by annotating the request longitude, latitude information of where I guess this car will be. Now, where does this leave us? This leaves us with a lot of applications, each tailor-made to a specific use case, but each also using a very different part of the network stack. One of these applications is IEEE 60911, electronic payment, first and foremost for tolling. There's SAE SPAT, signal phase and timing, which disseminates information about when traffic lights are supposed to, will be turning green, so making drivers aware of that so they can adapt their speed. There's ATC-CAM, cooperative awareness messages that I already talked about. This is reflected in IEEE SAM BSM, basic safety messages, the same concept really. There's ATC-DENIM, which is messages informing about events that have happened, disseminated using this geo-routing. But aside from all of these applications that can be put on the stack, this also opens up a whole lot of new opportunities. And one of the biggest ones, in my opinion, is the merging of in-vehicle and vehicle-to-vehicle communication. Now, for the first time, we can do sensor data fusion of local vehicle sensors and information received from other vehicles. So for any obstacle detected by a computer vision system, we can check if other cars have seen this as well, and vice versa. If some other car tells me there is an obstacle, I might try to double-check this using my computer vision system. And of course, this also opens a whole lot of security and privacy concerns of such a system, which William will be talking about very shortly. So that's it from me almost. If you need more information, if you want more information, I can advertise a textbook I authored on vehicular networking, which is geared for exactly that. We also have the IEEE Vehicular Networking Conference, so you are very invited to join us in Kyoto in December. or to just peruse the proceedings where much of what I talked about has been discussed about already and published in the shape of a scientific paper. So, thank you very much. Over to William.
Just make sure you get up here. Oops. I think I could drive.
Great. Thanks very much, Christoph, and thanks very much to the IETF for inviting us to present. It's an honour to be able to present to an organisation that's contributed so much to networking and communications across the world. So Christoph's given you a very good overview of what's been driving the adoption of cooperative ITS, and the ability to run applications to vehicles, the ability to avoid collisions and potentially save lives. As he mentioned, there's a number of security considerations that need to be dealt with. So the baseline questions that I'm going to be looking at are what is connected vehicle communication security? How is it different from other communication security? I mean, inside the IETF, there's a number of working groups on security in different settings. Why did we need to go and do something different? So also I'll talk about specific mechanisms that we're using and where these are located in the protocol stack. And the security challenges that we had to face in cooperative ITS, they include a lot of the usual ones. Confidentiality, integrity, authenticity, authorization, non-repudiation. These are standard security services that applications or communicating devices need to consume in order to make sure that they're getting the operations that they expect. Obviously, the specific requirements will often be application specific. So Christoph mentioned this cooperative awareness message where vehicles tell each other where they are. That's kind of the key message that enables collision avoidance. And obviously, you want everybody to be receiving that. You don't need confidentiality for that. Confidentiality gets in the way of the application working. But for other applications, such as any commercial transaction, obviously confidentiality is going to be very helpful. So we have these usual settings, these usual security goals, and they need to be applied in the appropriate way for your use case. Additionally, in the cooperative ITS setting, we have concerns like privacy. So if you have this radio in your car, and the plan in the US is that cars will be mandated to be equipped with these radios sometime in the 2020-2022 time period, you don't want that to give you automated speeding tickets. You don't want that to enable wide-scale tracking. So that's something that needs to be addressed. We have constraints on communications, on channel capacity. We have 10 megahertz channels, 6 megabits per second. It's not a lot if you've got a 300-meter range and potentially 200, 300 vehicles in that range all trying to communicate at the same time, especially with hidden node issues. So we need to ensure that the overhead, the communications overhead from security isn't too much. We also have constrained devices. Things in the automotive setting are expensive. You're building devices that need to have a lifetime of 30 years, that need to work in temperature ranges that you don't find in the usual server room. And some OEMs tell us that even a megabyte of automotive-grade storage is very, very expensive for them. It makes a difference to the cost of manufacture of the car. And some things that would be very easy to do if you had a gig of storage become very hard to do when you only have a meg of storage. So we've had to take that into account as well. As well as the fact that these devices might have relatively low-powered, relatively slow processors. There might be constraints on what HSMs, hardware security modules, you can include, again, because of the environmental and cost constraints. So we have those constraints, and additionally, we have the constraint that in the US again, we want to enable single radio devices for cost reasons. So we have these devices that are going to be very good at sending, not necessarily so good at receiving information from the internet in general. Those are devices that need to be kept up to date with their security information. They need to receive new certs as appropriate. They need to receive certificate revocation lists as appropriate. So yeah, there's a number of unusual challenges that you don't find in a general kind of internet protocol. I also want to flag some ways in which what we're doing is similar to things that have been done in IETF. There's some inaccuracies on this slide. I apologize for those. So there is I think it's a BOF at the moment on ITS IP over multi-hop in vehicular ad hoc networks. The ITS, I don't know what you call something before it's a WT, but the ITS group is working on that. They have a bar meeting after this, I think. We've also developed a different certificate format from X509, and there's a proposal to extend TLS to use that certificate in the handshake as well as the existing X509 certs. We do some automated certificate issuance techniques that are similar in spirit to what's going on in ACME, although, again, different technologies. We're doing some certificate management techniques that are similar to those that have been developed inside PKICs. And in general, I think it's fair to say that we're moving from the time when it was appropriate to focus on the things that were different about cooperative ITS to the things we're doing that have already been done in terms of certificate management, what goes on the back end, the management networks. And one thing I hope that we'll be doing over the next few years is working much more closely with existing technologies and existing technology groups to make sure that when it comes to cert management, we don't reinvent the wheel any more than necessary. So the specific topics I'm going to talk on in here, I'm going to talk a bit about the trust model, why we ended up developing a different certificate format from X509, what we use it for, and the threat model as well. I'm going to talk a bit more about those privacy concerns that I touched on earlier. I'm going to talk about security considerations for advertised services. So again, Christoph mentioned you get informed on the control channel that services are available on the service channel. What could go wrong with that? And also to talk about security considerations with geo-networking, this multi-hop protocol that's being used more in the European setting than in the American setting. So looking at the trust and threat model, there's been a lot of talk about the threat model for collision avoidance. You get in a message and that message alerts the driver and says, look out, a collision's about to happen, you should brake, you should swerve. Now obviously if you get a false alert, that's bad, but the question is how bad is that? If you get a message saying there's something bad just around the corner, swerve now, there's some cases, here, where there's the thing. There's some cases where swerving would probably be a bad idea. But in general, swerving is a decision that people take a small amount of time to make, and they take environmental considerations into account. And even if this were to be automated, again, you'd assume that the automated driving would take into account other sensor information, map information. And so we don't consider that a false positive, a false hazard alert is going to be directly hazardous to life, at least not in proportion to how the benefits of a correct hazard alert. At the same time, you don't want people to be plagued with false positives. One thing that they've discovered in the automotive industry with things like lane departure sensors, those cameras underneath the car, is that if people get more than 2 or 3 false positives a week, then they start to ignore the system, and if possible, they look for ways to turn it off. So we need to manage compromising the system such that the number of false positives people get can be kept to a manageable level, acceptable level. And so that means you can't have just anybody send messages. You need some kind of authentication on the message. But you can live with a small amount of compromise so long as you have mechanisms in place to manage the impact of that compromise. So that's your classical PKI approaches like certificate revocation. And then there's also potentially risk from false negative. You don't get an alert when you're in a hazard situation. And that's not going to be a problem for a while, but in 30 years' time, when we reach full penetration in the US, people do react to the to the circumstances they're in. There's some research that shows that people drove slightly more recklessly when seatbelt laws came in. There's research that shows that people drive closer to a cyclist wearing a helmet than a cyclist not wearing a helmet. And so people will adapt their behaviour to have expectations that this system works as well. Which means that if you're in a situation where there's some kind of denial of service attack going on, you don't get an alert, it's quite possible that in 30 years' time that will lead to more accidents happening than would happen under the same traffic situations today. So obviously that's a long-term problem. It does need to be addressed. Probably you need some kind of user interface notification that, look out, your collision warning system isn't reliable at the moment. Please pay attention. You should be paying attention anyway, but we mean it. Please pay attention. So that's the threat model that we're working inside. We want to authenticate messages, and we want to be able to revoke misbehaving devices. So when we authenticate, we're authorizing the message. We're saying that the sender is entitled to send the message. What's the trust model for that? It's application-based. So, for example, if I'm sending a basic safety message, that's identified by an identifier called a PSID, Provider Service Identifier, or in Europe it's called ITSA ID. PSID says this is a basic safety message, and my certificate says I'm allowed to send a basic safety message. It includes the PSID. And if there's granularity of permissions inside that application, those are encoded in the SSP, the service-specific permissions. I've got an example on the next slide, but essentially it's up to the CA, the certificate authority, that issues the certificate. When it issues the certificate, it has to check that the device requesting the certificate is entitled to those permissions that it's requesting. So looking at this example, you have the cooperative awareness message, here I am, and there's an extension defined to that that lets the sender claim to be an emergency vehicle and say, get out of my way, I'm a police car. So those are both identified by the same ITSA ID, it's hex 24. But if you have the null SSP in your cert, that means you're only allowed to send the here I am version of the message. If you have this 3 bytes 00040, then that also means you're entitled to claim to be an emergency vehicle. And the receiver of the message has to check at the application level that the SSP is consistent with the contents of the message. That can't be checked by the security services, because obviously the security services can't parse every individual application message. So this consistency check is part of the specification of the application itself. Any application that uses this model needs to say what is the consistency condition between different SSPs and the message contents. And again, the CA is in charge of checking that devices that get issued certs are entitled to those permissions. We talk about performance constraints. So channel capacity, to address that, we're using ECDSA, elliptic curve, digital signature algorithm with 256-bit curves. That's 64-byte signatures. That's to be compared to messages that are about 75 bytes long. So the overhead's quite large. And of course, you have to not just attach the signature, you have to attach the certificate, which itself typically has a signature as well. So the security overhead is more than 100% the size of the message itself. It's still small as security overhead goes for public key systems, but it is significant. In the US, we mitigated that slightly by allowing implicit certs. That's a technology that's owned by BlackBerry, where the signature bytes can be omitted from the cert itself. For intellectual property concerns, that's not being used in Europe at the moment. But it certainly mitigates a lot of the performance concerns we had in the US. Another performance concern is you can have up to 600 or more incoming messages a second, and even on a desktop PC you can't verify that many ECDSA signatures. So there's two options. One is you use hardware acceleration. That's the approach that the Europeans are in general taking. Another is that you filter messages before you decide whether or not to verify them. So if you're running a collision avoidance application, you look at all the messages and say, is this likely to indicate a collision? And if not, you don't bother verifying it. If it does indicate a collision, you verify it before you raise an alert to the driver. And obviously there's a gradation between the two. Those are the two extreme positions. But those are the way that we're managing the performance concerns. And to manage the concern that we had about it being easier to receive than to send to the CA, we've developed this nice technology which we call butterfly keys that use cool crypto that I can't go into, where a device can upload a single cert request at the start of its lifetime that allows the CA to generate an arbitrary number of certs for that vehicle that are unlinkable by any eavesdropper. And that lets us manage the peak load very nicely. The cert is just stored on the network. Whenever the vehicle gets its intermittent network connectivity, it can send up a short request saying, I'm ready for download now, and it can download all the certs that it's entitled to. Obviously, if it's been caught and revoked in that time, then it doesn't get new certs. On privacy, we don't want you to be tracked. We certainly don't want you to get an automated speeding ticket. Getting an automated speeding ticket needs to be addressed by legislation, unfortunately, because you are going around sending out your speed. But what we don't want is somebody who records you here and you here to be able to tell that those were both transmissions from you. And one way they can do that is record everywhere in between and reconstruct your trajectory. That's impossible to stop. And in fact, right at the moment, it can be done. Your automated tire pressure sensors give out a trackable wireless signal. So an eavesdropper who's everywhere already can track you. But an eavesdropper who's only in certain places, we don't want them to be able to do that. So one thing we do is you change your identifiers, your MAC address, application level identifiers. Those all change from time to time and simultaneously. For certificates, it's more complicated because you can't just generate a new certificate on the fly. You need to get it from a CA. So the model at the moment is that every vehicle is issued at least 20 certificates that are valid for a week, and it can adopt its own strategy to change between them. It can change every 5 minutes. It can change after the first 5 minutes, and then again when it's getting to a known destination, it can do some other strategy. And 20 certificates is a minimum. Many vehicles we hope will have more, and that lets the vehicle break up its track and hopefully confuse the attackers who can record you here and here, but not in between. Obviously, if you're issued a lot of certificates, if the CA knows that all of those certificates have gone to you, then an insider at the CA can track you. Or if the CA database gets compromised, anyone can track you. And so we split up the cert issuing process into a number of different components such that no individual component knows the collection of certificates that have gone to a particular car. The CA produces certs in an order determined by the RA, so the CA doesn't know which certs go together, and then it encrypts the certs back to the vehicle and sends them to the RA for distribution. So that, again, no component knows which cert belongs to which vehicle, and no component knows which collection of certs go together. But we've built in interfaces to allow revocation. Under certain circumstances, you can do what's called student and resolution, where correctly formed requests from one component to another will let you say, okay, these two certs go together, and we have a compact revocation system where you can issue a single entry on the revocation list, and that revokes all certs for that vehicle. Although one thing that's nice is that if you're revoked at time t, you can be tracked going forward from that time, but your movements before that time remain private. So if you started driving in January and your car was compromised in June, your movements from January to June are still private. So it's all a bit about the more complicated communications models, geo-networking, service advertisement. Geo-networking, Christoph talked about a little. Messages can be multi-opt. A single device can create a message and other devices will forward it over the network. Now, obviously, that's a classic denial of service scenario. I can produce a single message, and as a result of that, a large number of packets are produced. And that's managed partly by congestion control, but also by security, by communication security. When I create a message for forwarding, I have to sign it, and it has to be verified before it's forwarded. And this is actually the reason why the European model believes in a higher throughput of verified messages than the American model does, because geo-networking is baked into the system so much. And that's a nice way of reducing congestion, and it has a further cute optimization, which is that if you're signing at the network layer anyway, and if those packets aren't going to be forwarded onto some other medium, then you don't need to sign at the application layer, because the packets come from a single trusted source, so the one signature guarantees the entire thing. So if you look at a kind of high-level software architecture of the OBE, the onboard electronics, onboard equipment, in Europe and America, you see that by and large, Europeans who talk about CITS security talk about it as something that happens at the network layer. Americans, or people who work in America, talk about it as something that happens near to the application layer. Christoph also talked about service advertisements, and they have their own security considerations. So you're driving along, and node by the side of the road says you can stop here for electric vehicle charging information, point of interest notification. There's high-speed tolling, or not even necessarily stop here. You can consume as you drive past. And it also says if you go to this service channel and access this service, here's how you set your channel access parameters. Now, there's a number of possible risks there. One is that you simply get advertised a service that is phishing. You get advertised a service that's being run by a bad guy, and you exchange your data over that service, and they learn things about you. That's not the service advertisement's job to solve. If you're deploying a service, it's your job to secure. The service advertisement just says the service is available. And the service advertisement may in fact advertise a service that's running on some other device altogether. So we don't consider that the service advertisement can take responsibility for making sure all advertised services are good. So buyer beware. There's going to be a consistent theme. Another problem is if somebody advertises a bad service, that gets in the way of valid services. So an example is somebody advertises tolling on the safety of life channel. So everybody goes to the safety of life channel, they exchange tolling messages, and the congestion means the safety of life messages don't get through. So it's a very straightforward denial of service attack by creating false traffic on the channel. And there, again, that can't be addressed by signing anything. That has to be addressed by policy. So all devices in the system need to know what you're allowed to do on what channel, and they need to enforce that themselves so that bad advertisements of those type are ignored. And developing that policy is an ongoing project that, to be honest, isn't complete yet. And finally, there's the risk that responding to a service compromises your privacy. So if I consume a service that hardly anyone consumes, then the fact that I respond to it means it was me. And here again, we're kind of going buyer beware. That if you're choosing to sign up for that service, then you're choosing that you're doing it in the knowledge that there's a potential privacy violation from the fact that you're one of the few people using it. And it's up to you to manage that, to choose to consume the service not very often, or to find some proxy to obscure your service communications. So while that's fair to say, there's one outstanding research area, I think, in privacy, which is privacy for in the multi-application case. So a single application might be a fingerprint for my device. And it's fair to say, well, if you're using that application, take your own precautions. But if you have multiple applications such that the combination of them is a fingerprint for your device, it's not clear that individual applications can be expected to manage that properly. So it seems that down the road, CITS devices should support some kind of application separation, so an eavesdropper can't tell two applications are being hosted on the same device. A natural idea is that you have a separate virtual device for each of the applications. It's yet to be seen if that works, but that's a research direction I'm very interested in. So finally, this has been an info dump. There's a lot of stuff going on. We have a lot of unique constraints, a lot of points of contact with existing technologies. We've come up with a system that we believe meets very well the requirements of the day one applications and the constraints that we've got, but there's still a lot of future challenges. So one is integrate properly into for example, the Internet of Things security network. Cooperative ITS is clearly going to end up as a subset of M2M in general. So moving our mechanisms to fit into their frameworks is going to be a major project over the next few years to make sure that we can scale the way we want to. We need to manage congestion in an adversarial setting. That's going to be very difficult, not least because denial of service might have real impact in the future. So that's something that needs to be researched. We need to harmonize policy about which applications can use which channels. We need to learn more sophisticated communications model. You really extend this geo-networking idea, load groupcast, that kind of thing. And our final problem that no one's solved yet is that we're using ECDSA. If a quantum computer is invented, that means that all ECDSA signatures can be forged. Cars have a lifetime of 30 years. Who's to say there won't be a quantum computer inside 30 years? But all other signature algorithms that are believed to be quantum safe are too big. So if you invent a quantum safe signature scheme with short signatures, then you may well see what you've invented be in every car in the world ever at some point. So there's an interesting challenge for you. Okay, thanks very much.
So thank you. One thing I'd like to observe before we open the mics for a few short questions, we're running a little bit behind, is this might be yet another example of a system that was built to do something but also carries IP packets, and it could be that becomes its primary use, as we have seen with some other systems that were built to do something else but also carried IP packets. So if we could keep the number of questions small but of interest to the large group, I'm going to open the mic lines. Henning.
Henning speaking. On the first presentation, this has somewhat unfortunate memories of WAP again, namely creating a special protocol and stack for just one application. So I wonder, particularly with the emergence of widespread 4G LTE for many of the applications that were indicated, the non-safety application, the non-vehicle-to-vehicle type applications, where this kind of feels like it's outdated before it even ever gets deployed.
Christoph, you want to handle that?
It kind of feels that way, yeah.
Closer to the mic.
Sorry. The basic problem with mobile networks is that they promise a lot. They will be, I think, hugely beneficial, especially in the face of market rollout of the system, because if nobody has an 11P device in their car, then, well, I'm the only one on the road. I need a cellular uplink to be able to benefit at all from the system. I do think they are not so good at working for safety in the near field at full deployment, because that would mean deploying a massive number of base stations alongside the freeways, alongside the highways, and also in the city, something that right now the cell sizes are just too large. The second problem that cellular mobile networks have is, first of all, you have a dependency now built into the system. You are dependent on the operator of the system to not charge you or to charge you at reasonable rates, and to allocate a reasonable amount of spectrum to you. LTE can deliver extremely low delays at extremely low latency if sufficient resources are allocated to this use case. And that will be very interesting to see how this plays out in a real-world deployment.
Dave?
They were all ahead of me, but okay. Dave Crocker. So the question of security, this was a fascinating talk, difficult, extensive topic, diligent consideration. Thank you for that. My question is about practicality. Reliability, scalability, and performance. You touched, of course, on all of those, but my sense is that we have had no production mechanisms in this space, I don't just mean mobility, I mean in terms of security, that have approached anything like the scale or performance requirements that you've cast? And if I'm wrong, I'd like to hear about that. And if I'm not, is there any basis for knowing when we're going to be able to meet the criteria that this kind of system is going to have?
Yeah, so that is a valid concern, especially given the unique constraints of the automotive environment. There's a number of different hardware vendors. I could name 3 off the top of my head. NXP have in fact announced that they're developing silicon or they're developing the ability to make the necessary hardware in the necessary volumes. Will it work? Well, we've got some time to find out. GM are deploying in 2017. The bulk of American deployment isn't going to be till 2020. And this, to be honest, the question of scaling is something that's fairly low on the list of concerns that I hear about, because these are by and large silicon vendors who are already in the automotive industry, who already have experience making secure devices, maybe in different sections of the company, but the general assumption is that these are organizations that know what they're doing, and I would say we'll find out if they actually do.
Okay, at this point I want to close the mic lines to make sure we have enough time for the things that are coming up. Next.
Alistair Woodman, one question and a comment. So question is, have you thought about putting cost metrics in the messages to stop spamming and other types of overuse? I think that was probably a big failure in some of the technology that the IETF developed and internet in general. So have we cost metrics in email, for instance, we wouldn't be suffering from a spam problem. So that was my question. Have you thought about that? Second one, observation was, I understand that if you cross the bridges or the tunnels in New York, they track the toll tags and all those other types of information. And one of the first things that lawyers do in divorce cases is immediately subpoena this information. What possible belief do you have that this is not going to be used against most drivers of cars in the future?
Yeah, so those are 2 good questions. On spam cost, so if you're looking at single hop safety of life messages, there's no kind of proof of cost you can put in them that would really help, because the damage is done when they're sent and they tie up channel capacity. So, but it's an interesting idea potentially in geo-networking. It's one that I don't think is being considered. It might be more effective, in fact, than signing. That's certainly one to look at. As far as privacy goes and subpoenaing your routes, again, that's a great point. Yeah, I think the thing to bear in mind is again, especially in America, the government's aware that they're mandating this, so it's going to be looked on very suspiciously, and that the whole purpose is to save lives, and the effectiveness in doing that goes as the square of the penetration rate. So 1% of people at the margin who turn it off results in a 2% drop in effectiveness. That's not what you want. And so, there's a limit to what the federal government can do. That kind of law is made on a state-by-state basis, but everyone that I talk to takes very seriously the idea that statements should be made as strongly as possible. This won't be used for law enforcement. It won't be subpoenable. There's a line. We have these Amber Alert systems in the US where if a child gets kidnapped, then that information gets widely broadcast. Would that lead to a car being revoked from being tracked? That's yet to be decided. That's just hypothetical. So it's clear that there's a grey area. But at the same time, everyone is very serious about not doing anything that would hurt people's faith that this is purely intended to be a safety of life system.
Dan.
Dan York, relaying for somebody in the Jabber chat room, but I'll also say I appreciate the presentation. Personally, while I look forward to some of the convenience, the security and privacy issues certainly are concerning. But the relay is from Balaji Lengyol from Ericsson, and he asked the question remotely, will it be a government requirement to allow vehicle tracking like we have lawful interception today? So will it be a government requirement to allow vehicle tracking?
Yes, I think I just answered that. The intent is to do as little as possible that would detract from its use of the safety of life system, including hurting public faith in it.
Christian
Wittemer, Microsoft. I really appreciated your presentation of privacy issues and how you have this system of having multiple certificates to mitigate tracking. And that's an issue that we're going to find in other systems, not just vehicles. I mean, you could see people tracking various wearable devices and stuff like that. So that's a question for us. I mean, do we have any plan to carry that kind of technology in other IETF working groups and for other domains?
I don't have plans, but if the technology is useful, I mean, it's all published, it's all public. None of it is subject to patent, with the exception of implicit certs, which are going out of patent shortly. So it's available for use, and I'm very interested in talking about other ways it might be used. I mean, bear in mind that we're building this PKI that's going to be capable of issuing 1,500 certs, or sorry, I can't multiply by 20 now. It's going to issue 1,000 certs a year to every vehicle on the road, so it's going to have massive scale, and it should be possible to also use that for other applications. So the infrastructure will be there to support other uses, and I'd be very interested in exploring what those other uses might be.
over here, please.
Thanks, Russ. Robin Wilton from the Internet Society. I'm grateful to the panel for raising a number of the ethical issues that clearly crop up in this domain. So far, my experience has been that the discussion of those issues has been around fairly simple problems, like what happens when a vehicle has to choose between running over 4 pedestrians or injuring the driver. I think we need to go further than that. For instance, at what point will the algorithms in a vehicle perhaps decide to crash into another manufacturer's vehicle instead of one of their own, or to crash into the less insured or the person with the worse lawyers or the higher net worth. So I'm interested to know whether you're aware, the panelists are aware of any industry initiatives to explore some of those more nuanced ethical issues and the development of the algorithms that will put them into practice. And clearly this is an interest of mine and through my work in the Internet Society. So if anyone is interested in looking at those issues, I'd be delighted to hear from them.
Yeah, I mean, it's a very interesting topic. It's more automated driving than this driver alert use that we're thinking about at the moment. Obviously, those two are going to merge as time goes on. Right now, with the mandate coming down the pipe, people have really been focused on just getting the things to work. There's been a lot of banging metal boxes off walls. But clearly, it's a topic a lot of people have been talking about, and over the next 10 years, I think you'll see people really getting into it.
I'm sorry, I previously closed the mic lines, Randy. Bob?
Hi, Bob Hinded, Checkpoint. 2 things you said, or one of you said, that bothered me. You have 3 currently radio standards for this, like per geographic region. That's really broken. Come on, just one. I mean, I'm not a manufacturer of any of this, but this is just, you bang heads and get that together. The other is the discussion about the limitations of the computers you can do with these. I mean, you can do a Raspberry Pi for $35. It's the amount of processing, memory, storage you can get. Those curves are going down so quickly. If you limit your design to what you're hearing from the current manufacturers, it's going to severely limit what you can do. You should be pushing on this and assume it's going to get a lot better very quickly.
Christoph, you want to handle at least the first part of that?
The only thing I can say is I wholeheartedly agree. I mean, the good thing is the lower layers are settled. So the PHY, the MAC, that is common to all of them. The upper layers, they differ by a lot, yeah. And that has to change.
Okay, last one, Charlie.
I'm Charles Perkins, yes. I have 2 hopefully very quick questions. One first is, I really enjoyed the presentation, and presumably there's part of the motivation is to get work going in the IETF, but isn't this an area where there would be a lot of, let's say, impact from possible government regulation and requirement? And the second question is that it seems to me that there's a really large difference between making solutions for cars that I drive and cars that are self-driving. So I wonder if you have any comment about whether these would be actually two distinct efforts.
Christoph, you want to handle at least the first of those?
On the higher layer, I do think so, yeah. On the application layer, there will be huge differences, I guess, depending on who this information is for, if it's a human or if it's an automated vehicle. On the Phi and Mac, obviously they don't care, and I think even in between, the changes are not so large that need to be made if the stack is built in the right way. And that goes back to oh, now he's gone. That goes back to the previous question. The stacks have to be aligned very much towards being future-proof and towards being sensible in scale. Right now we have one stack that is pretty much bare bones and one stack that is trying to solve everything and standardize everything. So I really think the future should lie somewhere in between.
Thank you.
Okay, one more time, could we thank our speakers? And